Okay, perfect. So I was asked to shortly present my model and then present how I implemented the model so that it can fit on the VLab and how I uploaded it to the VLab and made everything work. So I'm first gonna shortly introduce the model. I did a metapopulation model, which is based on the paper of Hansky in 1998. Metapopulation model is basically a population of populations. So we are not interested in the survival of a focus of an individual, but we are interested in the survival of a focus species in the whole landscape. And we are interested in transit states. So what's happening between the states and between the end or after climate change and before climate change. So during the transition, not only at the end states. What I'm going to present today is also based on the paper by Rybicki and Hansky in 2013, where they implement the same model, but as a grid. So we can use, for instance, Earth observation data. So instead of working with patch area, we're going to work with a certain fitness. So each cell has a fitness that the species has for the given cell. And the model is defined as a specially explicit stochastic patch occupancy model, which is a Markov chain that goes from different occupied or unoccupied cell states and has transition probabilities. So the model is in this state basically a probability transition. So we have the probability to go from empty to occupied or from occupied to empty with a certain probability C or E. And the coization is mainly dependent on the dispersal from adjacent occupied cells with this kernel of dispersal from from surrounding cell multiplied by occupied cell, and where the fitness of the surrounding occupied cells plays a role. So the fitter a species is in a given cell, the more propagals it's gonna send out and basically colonize a new empty cell. The extinction is only dependent on the fitness of the given cell itself. So the species is gonna go extinct with a certain with the function which depends on the fitness. So the lower the fitness, the higher the value EI. The fitness is basically a Gaussian. This is from Rybicki 2013. So we have that the patch or the cell has a given quality. The species has a certain optimal quality phi and a certain niche around this optimal quality. So in our case, we want the species to have a fitness which is given by a combination of Earth observation inputs. And in the simplest case, which we are using now, or which we implemented now, we basically use a DEM with a certain, with the altitude being the fitness. So we have here ZI, which describes the altitude or the elevation and optimal elevation, and there a niche around, or an elevation range around this optimal elevation, which defines the fitness of the species. So just a short small example. This is a synthetic landscape called NoCN with a certain elevation distribution. We can see that for a certain optimal elevation and a certain niche width, we have given fitness in the landscape, and for other combination of parameters, we have other fitnesses in the landscape. So the model itself has been written in Python 3. I'm using different libraries of Python, NumPy for algebra, obviously. Then I'm using JIT, which is a library from NumPy, which precompiles certain functions so that it's faster at execution. I'm using Pil, or for Python 3, it's actually Pillow, to load and create the TIFF files. So the TIFF as input, the DM TIFF as input, and then it produces the average presence over several runs as a TIFF file. So for now, we have that the user can specify any given DEM as a link. It will then run the model with a given set of parameters. We have here sigma, so the niche width, which is equal to 10, the optimal elevation 2500. We have dispersal equal 5, coincidence 15, and extinction 0.1. The idea is that these parameters in future implementation of the model will either be calibrated or that the user will enter them manually based on literature or something like that he can then run in the model. Then the output shows, as for now, the average presence of a species in the landscape over 10 Markov chains at the final state. So this is the graphic from the VLab, which shows how it works. So we have that the DM is fed in the model. The model then runs and produces an average map. So this is the implementation, the view from the VLab. We see that on the top, we specify the location of the TIFF of the DM. Then the model is running the 10 runs, Markov chains, and at the end it produces the average map. So this is a random DM I found on the internet as an example. This would be the input with different elevation ranges, and this would be the average presence of this given species. So here is my feedback of the documentation. It's very well written and easy to follow. I think a better distinction between general cases and example would be needed or would be useful, so that we also have in general terms what each command should be and not specific to the example. I think it would be nice to have a small introduction on how and why each module is used. So how Git, Docker, and the local folders interact together. Also, where the different files are stored and how they are used. For instance, what's happening when the Amazon cloud copies the files, and where the root folder is, etc., so that it's easier to understand how the commands should be written for model execution. Yeah, maybe we should make the important commands more visible, for instance, with a different color scheme. And also, one thing I lost a lot of time on is make it clear that inside the Docker, we should use the Conda environment and not try to install all the libraries manually like I tried to do, which was actually a bit stupid. Anyway, so for the model porting, I still need to expand the input possibilities. I think, for the model porting, so from your side, I think it would be nice to expand the input possibilities. So for instance, having the possibility to choose parameters or stuff like that. Then maybe also add the possibility to change your model afterwards if you made a mistake, like edit the model and not having to delete it and resubmit the model or something like that. Then I think the added feature show model log for the developer is very nice. It makes it a lot easier to understand what's going on. And from my point of view, thanks a lot to Maltia for the help for the implementation. It was very useful, and I also learned a lot from that. And I think once implemented, the VLAB is actually very easy to use, and the interface is very straightforward. So that's really nice. So from my side, the missing features, I need to expand the Earth observation inputs. I also want to define sub areas so that not the whole DM is run, because you're not necessarily interested in the whole surroundings, but certain coordinates or shape files would be possible to limit the area. This would also make the execution of the model a lot faster. And then I would like also to calibrate with data so that the user can automatically calibrate with data or choose parameters, depends how far we get. That's all from my side. Thanks a lot for your attention. If you have any question, I'm happy to answer them.
Thank you very much,